Thank you. Yeah, my name is Josephine Holstein, and I'm one of the founders of Evoralis, and we develop enzymes for a circular plastic economy. The plastic's life cycle is far from being circular, as plastic products are still predominantly made from virgin fossil feedstocks. Each year, 353 million tons of plastic waste are generated, mainly emerging from packaging and textiles. Currently, only 9% of this waste is recycled and the rest goes to landfill or is incinerated. The main recycling approach is mechanical downcycling to lower quality products. 2% are chemical approaches, which often produce low quality oils by using large energy input, or they use toxic and expensive catalysts. A green alternative approach is the use of biocatalysts, which are also called enzymes. The biodegradation of synthetic polymers produces pure monomers, which can be recovered, purified, and repolymerized to virgin-grade materials. Enzymes are highly specific. They can work at room temperature, and they can deal with mixed and soiled samples. It has been estimated that the enzymatic monomer production uses up to 83% less energy, and around 0.5 gigatons less greenhouse gases are emitted in the supply chain. The whole process is scalable and can replace the use of crude oil. To establish industrial enzymatic recycling processes, the most difficult part is to find efficient enzymes. A few enzymes have been identified that can depolymerize plastics, but so far only one of them is efficient enough to be used industrially. The production of enzymes at multi-ton scale, as well as the infrastructure for enzymatic recycling processes at scale, exists. We developed an ultra-high throughput screening approach to find and improve efficient enzymes for plastic depolymerization. You can find enzymes in nature or public databases. You can generate huge enzyme libraries from environmental samples, even plastic contaminated areas. Conventional methods use low throughput methods to screen those libraries, for example, bacteria selection on plates. These methods are often time consuming and lack sensitivity. In silico-based selection methods are based on no functional data, and often further assays are needed. We developed a high-speed screening approach based on microfluidics. We generate water and oil picoliter droplets, where each droplet represents a reaction chamber. We generate thousands of droplets per second, so the video you can see here is slowed down 1,000 times. We screen 10 million enzymes per day, which is 1,000 times faster than any current method. With our technology, we developed a completely new PET hydrolase and improved it 5-fold. We filed the patent application for our technology and those enzymes in May this year. Our initial focus lies on the development of enzymes for the polyester PET, polyurethane pure, and polyamides PA. These plastics have a market share of 21%. In addition, they cover 90% of synthetic fibers used in textiles. They are also important in packaging, automotive, and construction. The potential market value of monomers generated from plastic waste is huge. The global waste comprises 353 million tons per year, and the value of the corresponding products that can be generated enzymatically is $248 billion. The global waste for PET, PURE, and PA is 74 million tons per year, and the value of the corresponding monomers is $92 billion. For Europe and the US alone, the PET, PURE, and PA waste is 29 million tons per year, and the monomers would be worth $38 billion. During the first 2 years, we would provide enzymes as a service to generate first revenues. Afterwards, we will sell our enzymes to customers in non-competitive areas.
You have 1 minute, just so you know.
We are also considering to develop our own biorecycling process for textile recycling. From the monomer cells, we expect to capture 20 million after 5 years and 300 million after 10 years. We are planning to raise £2 million to develop our blockbuster enzymes, set up a lab, and build out the team within the next 2 years. Currently, our team consists of 6 people with experts in chemistry, biology, microfluidic screening technologies, and protein engineering. Our CEO has more than 30 years of experience in high-tech commercialization. With this, I would like to thank you very much for your attention, and I'm happy to discuss further.
Awesome. Thanks for nailing the pitch, Josephine. You got it. 10 seconds on the clock. Very good. Very good. Let me bring in our other panelists here. I'll bring back Matt and Ben. And this time hand things over to Matt with Anthro. Matt, do you have any questions that you want to ask Josephine?
I do. A couple comments and then a question. So I love circular economy stuff. That's a big green check mark for me. I just think it makes sense. So I like your approach. And this is obviously a huge problem that you're addressing. My questions are all about go-to-market, which is a little early for you, right? Like I'm not usually asking that at pre-seed and seed stage level kind of stuff, but who are your beachhead customers? Like who do you sell to and why are they going to say yes to you? Because it's going to be disruptive to them. They're going to have to do things different. That's always hard, right? So what do you think?
Yes, so yeah, the customers eventually would be, there's different routes, but we are talking to all kinds of different people. So we talk to recycling companies, like big ones here, like general waste recycling companies here in the UK, but we are also, as we would like to focus on the textile market first. So we're also talking to companies that recycle textiles and the end customers, of course, would be, for example, in case of the textile recycling, would be big retailers that would use the recycled plastics in the end. And yeah, currently we are talking to all of these, and we are also trying to understand the supply chains and identify the customers.
Yeah, the supply, breaking into that supply, that value chain is going to be the big challenge for you guys. I good luck. I want you to succeed for sure.
Yeah, what I can also add to this, the enzymatic recycling process in general doesn't exist at the moment. So currently there's one company in France, they also establishing enzymatic recycling. But I think the barrier is to enter this market, but we are really confident that enzymatic recycling approaches is the way to go in the future.
All right, thank you.
Maybe let me allow also to go a very similar point, actually, like Matt, but from a slightly different angle. So I think it's well understood that it's complex and how you can penetrate that. But also the presentation, one thing I think you haven't been striking on enough, which I recommend you do, is the microplastics issue, because it's really the littering of the plastics which drives the circularity more than the availability of recycled feedstocks. That, in my view. So you can stress on that point much more than you have. But coming back, the one key issue might also be that it's the sorting of those different plastics. They don't come typically clean in one section. So having the right enzyme might be great. But how do you see it mixed materials? It not only composites based of different plastics, how you want to degrade them, and the other thing is in a mixed bag of waste. How can you tackle that? And then the second piece to that, it always typically comes with impurities or toxins for the enzyme. How do you conceive tackling that?
Yeah, so that's the advantage of enzymes. So they are highly specific, and if they are developed for specific plastics, they would, in a mixture, they would just identify the plastics that they are made for. So if you have a highly efficient enzyme for PET, for example, in a mixture of textile fibers, it would just degrade the PET. But we would like to tackle different types of enzymes specific for different types of plastics. And then you can apply either all of them together as an enzyme cocktail, for example. Then all the plastics would be degraded together, which makes it a bit more difficult to purify the monomers in the end. So you could also apply one enzyme after the other and get the pure monomers out afterwards. For enzymes, you can, we evolve them. So, I mentioned that briefly in my pitch. So enzymes, we can find them. So we identify completely new enzymes from environmental samples. We can find them in databases, but we can also improve them. So enzymes that you would find from an environmental sample, they might not be efficient enough for industrial applications. So we can perform directed evolution in the lab, and we can make them specific for any kinds of conditions. So they at higher temperature or lower temperature, different pHs, and also additives and impurities that you mentioned during your question as well wouldn't be a problem for enzymes.
Got it.
How much optimization are you able to deliver with your evolution-based, basically you're optimizing the enzymes through each cycle that you're going through? How much in terms of initial enzyme results versus final enzyme results are you able to do for time, cost, etc., in terms of improvements?
Yeah, so I mean, that's the advantage of our technology. We can screen 10 million enzymes per day, and you can imagine you can have really large enzyme libraries, and the screening is really fast. So, I mean, we can go through, millions per day, and one screening round we can handle really quickly, although downstream we also need to, when we screen a sample afterwards, we also have to verify that our hits, etc. But I mean, one screening campaign we can do within 1 week, and then we do further tests afterwards, and then we can do different types of plastic and different types of conditions basically really quickly.
Does it make sense for you to commercialize each of the enzymes versus licensing the enzymes to larger players and just being the IP discovery engine?
So at the moment, what we discuss internally, we will sell our enzymes. So we will either, we will produce those enzymes and sell them to our customers together with the know-how. I mean, we will license the technology for the recycling, basically. So the know-how about the plants, how you can recycle the plastics together with the enzymes that we sell. So that's our model right now.
And what is the biggest risk that you see in the business personally?
The biggest risk in the business, I mean, like I said, so with the next 2 years, we will use to develop blockbuster enzymes. And of course, there might be a risk that we won't find efficient enzymes, but we really believe in our technology. We can screen millions of enzymes per day. We have the know-how about protein engineering and microfluidic technologies. So we are really confident that we will find those blockbuster enzymes.